Hey everyone, Lee here. I'm currently working as a solution architect at an IT corporation here in Japan. After the video series on the NVIDIA Certified Associate, Generative AI and LLMs, NCA-GENM, I'm excited to introduce you to a new series on the NVIDIA Certified Associate, Generative AI Multimodal, NCA-GENM, certification. Earning this credential is a great way to formally validate your foundational skills in designing and managing AI systems that work across various data types like text, images, and audio. It really makes your resume stand out and demonstrates to employers that you have a verified understanding of how to build these complex AI systems that can see, hear, and read. Are you excited and ready to earn this certification? Let's get started and dive into the questions for the NCA-GENM together. Question 1. After fine-tuning a large language model, LLM, for generating legal documents, what is the most effective way to assess whether the fine-tuning has improved the model's performance for this specific task? Measuring the speed at which the fine-tuned model generates text, regardless of content accuracy. B. Evaluating the model's output against a benchmark dataset of legal documents that it has never seen before. C. Comparing the fine-tuned model's output with that of a non-fine-tuned model on random text generation tasks. D. Testing the fine-tuned model on a set of common, non-legal text generation tasks to measure general improvement. Okay, so the core of this question is about validation. We've spent time and resources fine-tuning a model for a very specific purpose, creating legal documents. Now, how do we prove it was worth it? How do we know it's actually better at that one job? Let's look at the options. First, option A talks about measuring speed. This is an easy one to eliminate. Speed is great, but it means nothing if the output is garbage. We could have a model that generates nonsense at lightning speed, but that doesn't help us with legal documents. We need accuracy and relevance, not just velocity. So A is out. Now, let's look at options C and D together because they make a similar mistake. Option C suggests comparing our specialized model to a general model on random tasks. Option D suggests testing our specialized model on common, non-legal tasks. Both of these are wrong because they don't test the model on the task it was trained for. Fine-tuning is all about making a model a specialist. We don't care if it's better at writing poetry or random paragraphs. We care if it's better at writing legal contracts. Testing it on unrelated tasks doesn't measure its performance for the specific task the question asks about. This brings us to option B, which is the correct answer. Evaluating the model's output against a benchmark dataset of legal documents that it has never seen before. This is the gold standard for model evaluation. Here's why it's perfect. Benchmark dataset. This means we have a set of high-quality, correct examples to compare against. Of legal documents. This ensures we are testing the model on the exact domain we trained it for. That it has never seen before. This is the most crucial part. It tests the model's ability to generalize its learning to new situations, rather than just memorizing the data it was trained on. So, by comparing the model's new outputs to a golden set of unseen legal documents, we can objectively measure if the fine-tuning was a success. It directly answers the question of whether the model's performance for this specific task has improved. Question 2. When customizing a large language model LLM for a specific task, which approach is most efficient in terms of computational resources and time while still ensuring high performance? A. Using transfer learning by fine-tuning the top layers of the model on your domain-specific dataset. B. Retraining the entire model from scratch using your domain-specific dataset. C. Fine-tuning the model with only a few additional layers on a small dataset of examples. D. Customizing the model by manually editing its parameters based on trial and error. Okay, this question is all about the classic trade-off in machine learning. How do we get the best results without spending a fortune on computers and waiting for weeks? We want a solution that's both efficient and effective for a specific task. Let's get the really impractical options out of the way first. Option D, manually editing parameters, is just not feasible. These models have billions of parameters. Trying to change them by hand through trial and error would be like trying to paint the Mona Lisa by throwing buckets of paint at a canvas. It's chaotic, unscientific, and you'd never get a coherent result. So, D is definitely out. Option B is retraining the entire model from scratch. This is the complete opposite of efficient. Training a large language model from zero requires an enormous amount of data and a massive, expensive cluster of GPUs running for a long time. It's the most resource-intensive and time-consuming approach you could possibly take. It violates the core requirement of the question, so B is also incorrect. Now we're left with A and C, which both sound plausible because they involve fine-tuning. Let's look closer. Option C says, fine-tuning the model with only a few additional layers on a small dataset. While adding new layers, like adapters, is a valid technique, the description is a bit vague. More importantly, using only a small dataset might not be enough to ensure the high performance that the question requires. This makes option A the best answer. Using transfer learning by fine-tuning the top layers of the model on your domain-specific dataset. This is the classic and most widely used approach. The idea is that the base model has already learned a vast amount about language, grammar, and general knowledge from being trained on the internet. We don't want to lose that. The lower layers of the model hold this general knowledge. The top layers are more specialized. By only fine-tuning the top layers, we are essentially teaching an expert a new specialty. We leverage all the foundational knowledge and just tweak the final output to fit our specific need. This approach is much faster and requires far fewer computational resources than retraining everything, but it's highly effective because it builds upon that powerful pre-existing foundation. Perfectly balances efficiency and high performance. Question 3. You are building a generative AI model that needs to create personalized marketing content based on user data, including demographics, past purchases, and browse history. Which data preprocessing steps would most likely improve the quality and relevance of the generated content? A. Applying PCA, principal component analysis, to reduce the dimensionality of categorical variables. B. Scaling all numerical data to a range of 0 to 255 to mimic image preprocessing. C. Normalizing all numerical data and one-hot encoding categorical variables. D. Dropping all categorical variables and focusing only on numerical data. Okay, this question is about preparing our data for the model. We have what's called structured data, a mix of different types of information. We have numbers like age or how much someone spent, and categories, like which city they live in or what product category they browsed. The goal is to transform this mixed data into a language the model can understand and learn from effectively. Let's start by eliminating the options that are clearly bad ideas. Option D says to drop all categorical variables. This would be a huge mistake. For personalized marketing, knowing someone's browse history or past purchase categories is incredibly valuable. Throwing away this information would make it almost impossible for the model to create truly relevant content. So D is out. Option B suggests scaling numerical data to a range of 0 to 255. This specific range is used for pixel values in images. While scaling numbers is a good practice, using a range from a completely different domain like image processing is arbitrary and not standard practice for this kind of problem. It also completely ignores what to do with the categorical data. So, B is incorrect. Option A talks about using PCA on categorical variables. PCA is a technique used to reduce the number of features, but it's designed to work with numerical data, not categorical data like city or product type. You can't directly apply PCA to words or categories. This is the wrong tool for the job. So, A is also incorrect. This leaves us with option C, which is the correct answer. Normalizing all numerical data and one-hot encoding categorical variables. This is the standard and best practice for handling this type of mixed data. Let's break down why. Normalizing numerical data. This means scaling numbers so they are in a common range, like 0 to 1. It prevents features with large values, like annual income, from overpowering features with small values, like the number of items in a cart. It puts all numerical data on a level playing field so the model can learn their relative importance. One-hot encoding categorical variables. This is how we convert categories into numbers that a model can understand. It takes a column like city, with values New York, London, Tokyo, and turns it into 3 separate columns, is_new_York, is_London, is_Tokyo, with a 1 or 0 in each. This lets the model use the information without incorrectly assuming that one city is greater or less than another. By doing both of these steps, we ensure all the user data is converted into a clean, consistent numerical format that the AI model can use to learn patterns and generate high-quality, personalized content. Question 4. You are working with a multimodal generative AI model that processes both text and images to generate detailed descriptions of objects. The model consistently produces inaccurate descriptions when processing high-resolution images with complex backgrounds. Which 2 actions should you consider to improve the model's performance in handling high-resolution images with complex backgrounds? Select 2. Use grayscale images instead of colored images. B. Reduce the image resolution before feeding it into the model. C. Increase the model's learning rate to improve accuracy during training. D. Fine-tune the model using a pre-trained model specialized in object detection. E. Implement data augmentation techniques to diversify the training set with various background complexities. So, the core issue here is that our model is getting confused. It's looking at a picture with a lot going on, a complex background, and it can't figure out what the main subject is. It's like trying to describe a single person in the middle of a massive crowd. We need to help the model focus on the important part, the object, and ignore the noise, the background. Let's start with the options that won't work. Using grayscale images, as suggested in A, is not a good idea. Color is often a very important feature for describing an object, and taking it away removes key information. Similarly, reducing the image resolution, option B, is also counterproductive. You'd lose important details of the object itself, making descriptions even worse. Option C, increasing the learning rate, is a risky, nonspecific tweak. A higher learning rate can make training unstable and is not a targeted fix for the model being confused by backgrounds. This leaves us with the 2 correct answers, D and E. They work together perfectly to solve the problem. Option D suggests fine-tuning with a pre-trained object detection model. This is a brilliant move. An object detection model is already an expert at finding objects in images. By using this knowledge, we directly teach our model the skill it's currently missing: how to locate the object of interest first. Option E suggests using data augmentation. This is about making our training data better. If the model is bad at handling complex backgrounds, we can give it more practice by programmatically placing our objects onto thousands of different, random, complex backgrounds. This teaches the model to become robust and ignore distracting backgrounds because it has seen the same object in so many different contexts. By combining D and E, you're attacking the problem from 2 angles. You're explicitly teaching the model how to find objects, and you're giving it the practice it needs to learn to ignore distracting backgrounds. Question 5. The AI development team has deployed a multimodal AI application that generates automated reports from various data sources. After several weeks in production, users report that the application occasionally generates incomplete reports, especially during times of high server usage. What is the most effective strategy to identify and resolve this issue? A. Conduct a thorough performance profiling and stress testing to identify bottlenecks. B. Limit the application's usage during peak hours to prevent overloading. C. Reduce the complexity of the generated reports to decrease processing time. D. Add more redundancy to the server infrastructure to handle the load. Okay, so the situation is pretty common. We have an application that works fine under normal conditions but starts to fail when it gets busy. The key symptom is incomplete reports during high server usage. The question asks for the most effective strategy to both find the problem and fix it. Let's look at the options that jump to a solution without a proper diagnosis first. Option B, limiting the application's usage, isn't really a fix. It's like saying, "Doctor, my arm hurts when I lift it," and the doctor replies, "Then don't lift it." It avoids the problem but doesn't solve the underlying issue. The goal is to make the application robust, not to hide it from users. Options C and D are also potential solutions, but they are premature. Option C suggests reducing the report complexity, and D suggests adding more servers. Both of these might work, but they are just guesses. What if the bottleneck isn't the report complexity but a slow database query? Then simplifying the report won't help. What if the problem is an inefficient piece of code that one server can't handle, and adding more servers won't fix it either? Throwing money and resources, like more servers, or reducing features, like report complexity, without knowing the actual root cause is inefficient and might not even solve the problem. This is why option A is the correct answer. Conduct a thorough performance profiling and stress testing to identify bottlenecks. This is the only option that focuses on diagnosis first. It's the methodical engineering approach. Stress testing allows you to reliably reproduce the problem in a controlled environment by simulating high server usage. Performance profiling watches your application while it's under stress and tells you exactly which parts of the code, which database calls, or which system resources are slowing down and causing the failure. By doing this, you're not guessing anymore. You're using tools to find the exact source of the problem. Once you've identified the bottleneck, you can then apply a targeted and effective solution, which might be to optimize the code, add a database index, or, if necessary, add more hardware. But you do it with confidence because you've diagnosed the issue first. It's the most effective strategy because it ensures you're fixing the right thing. Question 6. You are developing a multimodal AI model that combines text, image, and sensor data. During training, you realize that the sensor data is significantly less frequent than the text and image data, causing the model to underperform when relying on sensor inputs. What is the most effective strategy to improve model performance in this scenario? A. Train separate models for each modality and ensemble them later. B. Use data fusion techniques to combine the modalities more effectively. C. Reduce the frequency of text and image data to match the sensor data. D. Increase the number of sensor data samples by generating synthetic data. Okay, so the problem here is a classic data imbalance, but across different types of data or modalities. We have lots of text and image data, but very little sensor data. Because of this, the model is basically ignoring the sensor data because it's so rare, and as a result, it doesn't perform well when that sensor data is important. We need to find a way to fix this imbalance. Let's look at the options that don't quite hit the mark. Option C suggests reducing the amount of text and image data to match the small amount of sensor data. This is a bad idea. You would be throwing away a huge amount of valuable information. This would balance the dataset, but it would almost certainly make the overall model much weaker because it has so much less to learn from. Options A and B are about the model's architecture. Option A suggests training separate models, and B suggests using different data fusion techniques. While these are important considerations when building a multimodal model, they don't solve the root problem. The root problem is the lack of sensor data. Whether you use one big model or 3 separate ones, the part of the system responsible for learning from sensor data will still be weak because it simply doesn't have enough examples to learn from. This brings us to option D, which is the correct and most effective strategy. Increase the number of sensor data samples by generating synthetic data. This approach, often called oversampling, directly addresses the core issue without making any sacrifices. Instead of throwing away good data, you create more of the data you lack. By generating new, realistic sensor data points, you can create a larger, more balanced dataset. This gives the model enough examples to properly learn the patterns within the sensor data, allowing it to contribute effectively to the final prediction. It strengthens the weakest link without weakening the others, leading to a more robust and better performing model overall. Question 7. You are designing a multimodal AI system that integrates visual data from medical images, e.g., X-rays, with corresponding patient notes to assist in diagnosing conditions. The system often overlooks critical details in the images, resulting in inaccurate diagnoses. How can you modify the system to improve its accuracy by ensuring it pays closer attention to relevant parts of the medical images? A. Use a pre-trained image classification model without fine-tuning it on medical images. B. Implement a spatial attention mechanism that highlights critical regions in the medical images. C. Increase the resolution of input images before processing. D. Apply data augmentation techniques to increase the diversity of the training data. So, the problem here is very specific. The AI model is looking at medical images, but it's missing the important spots. It's like it's glazing over the whole image instead of zooming in on the critical area that might signal a disease. We need to teach it how to focus. Let's look at the options that don't directly solve this focus problem. Option A, using a pre-trained model without fine-tuning would be a disaster. A model trained on everyday images like cats and cars knows nothing about how to read an X-ray. It needs to be fine-tuned on medical data to be useful at all. This would make things worse, not better. Option C is to increase the image resolution. While having more detail might seem helpful, it doesn't solve the core issue. If the model doesn't know where to look, giving it an even bigger, more detailed image might just give it more places to get lost. The problem isn't a lack of detail. It's a lack of direction. Option D suggests data augmentation. Data augmentation is a great technique to make a model more robust by showing it more varied data, like rotated or brightened images. It's a generally useful practice, but it doesn't specifically teach the model where to look inside an image. It helps the model generalize better overall, but it's not the most direct solution for making it focus on tiny critical regions. This leads us to option B, the correct answer. Implement a spatial attention mechanism. This is the perfect tool for this exact problem. An attention mechanism is a component you add to a model to teach it what parts of the input are most important. A spatial attention mechanism learns to assign higher importance scores to specific regions or pixels in an image. In this case, it would learn to highlight the suspicious areas on an X-ray, forcing the rest of the model to pay closer attention to them when making a diagnosis. It directly solves the problem of the model overlooking critical details. Question 8. You are working on a project that requires the integration of geospatial data, text data from social media posts, and images from satellite data to monitor environmental changes over time. Some of the geospatial data is incomplete due to satellite malfunctions, and the text data includes several irrelevant posts. What is the most appropriate strategy to ensure high-quality multimodal data integration for this project? Use filtering techniques to remove irrelevant text data and apply interpolation for the geospatial data gaps. B. Ignore the incomplete geospatial data and focus on the available text and image data. C. Fill missing geospatial data with the mean value and discard irrelevant text data. D. Use text-based NLP models to generate missing geospatial data based on social media posts. Okay, so this problem gives us a scenario with 3 data types, and 2 of them have quality issues. Our geospatial data has missing pieces, and our text data is noisy. We need to find the best way to clean up both of these issues before we can effectively combine all the data. A good strategy has to address both problems intelligently. Let's start by looking at the less effective options. Option B says to just ignore the incomplete geospatial data. This is a bad move because that data is a core component for monitoring environmental changes. Throwing it away just because some of it is missing would seriously damage the quality of our project. Option D suggests using NLP to generate missing geospatial data from social media posts. This is very unreliable. Trying to get precise map coordinates from informal text is extremely difficult and prone to huge errors. It's not a scientifically sound way to fill in gaps left by a faulty satellite. Now let's compare options A and C. Both of them correctly suggest getting rid of the irrelevant text data. The main difference is how they handle the missing geospatial data. Option C suggests filling the gaps with the mean value. This is a very basic approach that doesn't work well for geospatial data. For example, filling a missing temperature reading in a cool mountain valley with the average temperature of the whole country would be very inaccurate. The location matters. This makes option A the best strategy. It proposes using the right tool for each job. For the noisy text data, it suggests using filtering techniques, which is the standard process for removing irrelevant content. For the missing geospatial data, it suggests applying interpolation. Interpolation is a much smarter method than using the mean because it estimates a missing value by looking at the known values surrounding it. This respects the spatial nature of the data and provides a much more accurate and logical estimate for the missing points. So, option A provides a robust and technically sound approach for both cleaning the text and repairing the geospatial data, ensuring the highest possible quality for the final integrated dataset. Question 9. You are developing a multimodal AI model that integrates speech recognition, text processing, and image analysis to assist visually impaired users by describing their surroundings in real time. The model works well in controlled environments but fails to perform in noisy, real-world conditions. Which of the following adjustments is most likely to improve the model's performance in noisy environments? Increase the training data size by adding more images. B. Deploy the model on more powerful hardware. C. Implement noise-canceling algorithms in the speech recognition module. D. Use a more complex image processing algorithm. Okay, so the problem is very clearly defined here. We have a model that's great in a quiet room but fails when it's out in the real world where there's a lot of background noise. The key failure condition is the noisy environment. We need to find a solution that specifically targets this noise problem. Let's look at the options that don't address the core issue. Options A and D are both focused on the image analysis part of the model. Option A suggests adding more images, and D suggests using a more complex image algorithm. While these might improve the visual aspects of the model, they do absolutely nothing to solve the problem of background noise interfering with the audio input. The problem isn't what the model sees, it's what it hears. Option B suggests deploying the model on more powerful hardware. More power means the model can process data faster, but it doesn't make the input data any cleaner. If the microphone is picking up a lot of street traffic along with a user's voice, a faster processor will just analyze that garbled audio more quickly. It doesn't fix the garbage in, garbage out problem. This makes option C the only logical and correct answer. Implement noise-canceling algorithms in the speech recognition module. This is a direct and targeted solution to the stated problem. Noise-canceling algorithms are specifically designed to identify and filter out background noise from an audio stream, leaving a cleaner voice signal. By adding this to the speech recognition part of the model, you are directly addressing the reason it fails in noisy conditions. It allows the model to get a clear audio input to work with, which is the most critical step to improving its performance in the real world. Question 10. You are developing a software application that incorporates generative AI to assist developers by suggesting code snippets based on their written descriptions. The goal is to improve the accuracy of code suggestions based on varying levels of detail provided in the descriptions. Which approach best utilizes prompt engineering to enhance the generative AI model's ability to provide accurate code suggestions? Select 2. Use detailed and structured prompts that specify the exact requirements for the code snippet. B. Allow the model to infer requirements from vague and broad descriptions. C. Limit prompt complexity to only the most basic descriptions of the code needed. D. Train the model exclusively on code snippets without including context or descriptions. E. Provide feedback on generated code snippets to refine the prompt over time. So, this question is all about prompt engineering, which is the art of writing good instructions for an AI model to get the best possible results. We want our AI to be an accurate code assistant, so we need to figure out the best way to talk to it. First, let's eliminate the options that describe bad practices. Option D is about training the model, not using it. Prompt engineering happens when you're using the model, not when you're building it from scratch. So that's out of scope. Options B and C are examples of poor prompt engineering. Asking the model to guess from vague descriptions, B, or giving it overly simple prompts for complex tasks, C, is a recipe for getting inaccurate or useless code. You want to reduce ambiguity, not create it. This leaves us with the two correct answers, A and E, which represent the core principles of effective prompt engineering. Option A is about using detailed and structured prompts. This is the foundation of getting good results. The more specific and clear your instructions are, the better the AI can understand your intent. Instead of saying, write a function to sort a list, a good prompt would be, write a Python function named sort_users that takes a list of user objects and sorts them in descending order based on their age attribute. This clarity drastically improves accuracy. Option E is about providing feedback to refine the prompt over time. This describes the iterative nature of prompt engineering. You almost never get the perfect prompt on the first try. The process involves giving the model a prompt, seeing what it generates, identifying any errors or misunderstandings, and then modifying your original prompt to be even clearer. This feedback loop is essential for developing highly effective prompts that consistently produce the desired output. So, the best approach is a two-part strategy. Start with the clearest, most detailed instructions you can and then use a process of trial, error, and feedback to continuously improve those instructions. Question 11. You are conducting an experiment to evaluate a multimodal AI model that integrates text, audio, and visual data. During testing, you observe that the model's performance varies significantly across different test batches. What might be causing this inconsistency? Select 2. A. The model is being tested on a single modality instead of multimodal data. B. The test environment is not identical to the training environment. C. The model is underoptimized. D. Different test batches contain different amounts of data. E. Inconsistent preprocessing across different modalities. Okay, so the core problem is instability in our test results. The model gets a good score on one batch of test data, then a bad score on the next. This suggests the issue isn't necessarily with the model itself, but with the testing process. We're looking for two reasons why the results would swing wildly from one batch to another. Let's first look at the options that would likely cause consistently poor performance, not variable performance. Option B, having a different test environment, would probably make the model perform poorly across all batches. Likewise, an underoptimized model, as in option C, would just be a bad model in general, leading to consistently low scores. These don't explain the up and down results. This brings us to the two correct answers, D and E, which both describe inconsistencies in the testing process itself. Option E points to inconsistent preprocessing. This is a very common source of error. Preprocessing includes all the steps to get data ready for the model, like resizing images, normalizing audio, and tokenizing text. If these steps are not applied in the exact same way to every single test batch, you're essentially feeding the model differently prepared data each time. The model's performance will naturally vary because the quality and format of its input are inconsistent. Option D suggests that different test batches contain different amounts of data, or more broadly, a different distribution of data. Imagine your test set isn't shuffled properly. One batch might happen to contain all the easy examples, while the next batch contains all the hard examples. The model would score very high on the easy batch and very low on the hard one. This creates the illusion of inconsistent performance, but the real issue is that the difficulty of the test is changing from one batch to the next. So, both of these issues, inconsistent data preparation, E, and non-uniform batches of data, D, would lead to the unstable and varying performance metrics described in the question because the test itself is not consistent. Question 12. You are designing a multimodal AI system for a medical imaging application that needs to generate detailed reports based on X-ray images. The system must handle a wide range of medical conditions, and the reports must be accurate and comprehensive, including potential diagnoses, treatment options, and follow-up recommendations. Additionally, the system must prioritize the generation of reports for more critical cases. Which approach would be the most effective in ensuring that the system prioritizes critical cases while generating accurate and comprehensive reports? A. Fine-tune the model on a dataset with equal representation of all medical conditions. B. Implement a two-stage model where the first stage classifies the urgency level, and the second stage generates the report based on the urgency. C. Use a pre-trained language model without any additional fine-tuning, as it can generalize to any medical condition. D. Use reinforcement learning with a reward function that emphasizes the accuracy of the diagnosis. Okay, so this question describes a system with two equally important jobs. First, it has to write high-quality, accurate medical reports. Second, it needs to act like a hospital's triage system, identifying and working on the most critical cases first. A good solution has to do both of these things well. Let's start with the options that don't meet all the requirements. Option C, using a general model without any medical fine-tuning, is a non-starter. It would be highly inaccurate and unsafe for a medical application. Option A suggests fine-tuning on a dataset with equal representation of all conditions. While fine-tuning is good for accuracy, treating all conditions as equal is the exact opposite of prioritizing critical cases. Option D suggests using reinforcement learning with a reward for accuracy. This could be a good way to make the reports more accurate, but it only addresses the first part of the problem. It does nothing to solve the prioritization requirement. The system would get good at writing reports but would still have no way of knowing which one to write first. This is why option B is the most effective approach. Implement a two-stage model. This design is brilliant because it explicitly separates the two jobs. The first stage acts as the triage nurse. It's a fast, simple classifier that looks at an image and just answers one question. How urgent is this? It labels the case as critical, moderate, or routine. The second stage is the specialist doctor. It's a more complex model that takes the images and generates the detailed, comprehensive report. The system uses the output from stage 1 to manage its workload, putting all the critical cases at the top of the queue for stage 2 to process. This architecture perfectly addresses both requirements. It has a dedicated component for prioritization and another dedicated component for generating accurate reports. Question 13. A company wants to deploy a generative AI model that can analyze and generate text, images, and audio content simultaneously. The company has access to a large multimodal dataset and powerful hardware but needs to optimize the system architecture to meet the needs of both real-time processing and high-quality generation. Which two components are most critical for optimizing the performance of a generative AI system that handles multimodal data, text, images, and audio, to ensure real-time processing and high-quality generation? Select 2. A. Traditional CPUs with multiple cores. B. Custom AI accelerators, e.g. TPUs. C. High-performance GPUs with tensor cores. D. High-bandwidth memory, HBM. E. Solid-state drives, SSDs, for data storage. Okay, so this question is asking us to pick the two most important hardware components for building a top-tier AI system. The keywords are real-time processing and high-quality generation. This means we need a system that is both incredibly fast at computation and can handle the massive models and data required for high quality. Let's think of this like building a high-performance race car. First, let's look at the options that are important but not the most critical for a race. Option A. Traditional CPUs are like the car's dashboard and electrical system. They're essential for the car to function, but they're not the engine that makes it win the race. CPUs are too slow for the heavy-duty parallel processing that AI requires. Option E. SSDs for data storage is like the garage where the car is kept. Having a fast way to get the car out of the garage is good, but it doesn't affect the car's speed on the racetrack itself. The main bottleneck isn't loading the model from storage. It's the computation during real-time use. Now let's look at the core components. We need an engine and a fuel system. Option C, high-performance GPUs with tensor cores, is the engine of our race car. GPUs are specifically designed for the kind of massive parallel calculations that are at the heart of AI. The tensor cores are a further specialization within NVIDIA GPUs that make them even faster at these specific AI operations. This is the component that provides the raw computational power needed for real-time performance. Option D, high-bandwidth memory or HBM, is the high-performance fuel injection system. You can have the most powerful engine in the world, but if it can't get fuel fast enough, it's useless. Large AI models and multimodal data are huge. HBM is a type of ultra-fast memory that sits right next to the GPU, feeding it data at incredible speeds. This ensures the powerful GPU is never waiting for data and can run at its full potential, which is critical for both speed and generating high-quality results from large models. While custom AI accelerators like TPUs, option B, are also like powerful engines, high-performance GPUs are the more common and versatile workhorse in the industry for these tasks. Therefore, the most critical combination for this system is the powerful engine, GPU, and the high-speed fuel system that keeps it running, HBM. Question 14. You are developing a multimodal AI system that combines image recognition, text analysis, and natural language processing to assist in evaluating loan applications. The system must make fair decisions across applicants from different socioeconomic backgrounds. What is the most effective strategy to minimize bias in this AI system? Using historical data on loan approvals without modification to maintain consistency. B. Incorporating fairness constraints during the model training process to ensure balanced outcomes for different demographic groups. C. Training the model on data from a single region with a homogeneous population to simplify the system. D. Prioritizing the accuracy of predictions based solely on applicants with high credit scores. This question is about a very important topic in AI ethics: how to build a system that is fair. The goal is to evaluate loan applications without discriminating against people from different backgrounds. We need to find the best strategy to actively reduce bias. First, let's identify the strategies that would actually create or increase bias. Option A, using historical data without modification, is a classic recipe for a biased AI. Historical loan data often reflects past societal biases, and if you feed that data directly to a model, the model will learn and likely amplify those same unfair patterns. Option C, training on data from a homogeneous population, would create a model that is an expert on only one group of people. It would be inherently biased against anyone who doesn't fit that narrow profile. Similarly, option D, focusing only on applicants with high credit scores, would train the model to be good at evaluating one specific group, likely leading it to unfairly reject applicants who are qualified but don't fit that perfect mold. This makes option B the only correct and responsible approach, incorporating fairness constraints during the model training process. This is a proactive technique where you explicitly tell the model that fairness is part of its goal. During training, you don't just tell the model to be accurate, you add mathematical rules that force it to check its own work. For example, a constraint could require the model to have similar approval rates for qualified applicants across all demographic groups. This forces the model to find a solution that is not only predictive but also equitable, directly addressing the core requirement of minimizing bias. Question 15. You are developing a multimodal AI model that combines text and video data. You notice that the text data has varying levels of quality and includes multiple languages, while the video data is consistently high quality but from different domains. Which pre-processing steps should you take to ensure the model can effectively utilize both data types? Select 2. Translate all text data into a single language. B. Normalize the text data by converting all text to lowercase. C. Perform domain adaptation on the video data. D. Crop the video data to reduce processing time. E. Standardize the frame rate of the video data. Okay, so this scenario presents us with two distinct problems, one for each data type. For the text data, the main issue is that it's in multiple languages. For the video data, the main issue is that the content comes from different domains like sports, cooking, or news. We need to pick one solution for the text problem and one for the video problem. Let's start with the text data. The most significant issue is the mix of languages. Option B, converting text to lowercase, is a standard cleaning step, but it doesn't solve the language problem. A model will still be confused by the different vocabularies and grammar structures. This makes option A, translate all text data into a single language, the correct and most crucial step. By converting everything into one common language like English, you create a consistent and uniform dataset that the model can understand and process effectively. Now for the video data. The challenge is handling content from different domains. Options D, cropping, and E, standardizing frame rate, are basic technical adjustments. They help with consistency but don't address the core problem, which is that the model needs to understand the context of a sports video differently from a cooking video. This is where option C, perform domain adaptation on the video data, comes in. Domain adaptation is a specific set of techniques designed to help a model that was trained on one type of content, domain, to generalize and perform well on other types of content. It's the most advanced and appropriate strategy for handling the variation in video domains. Therefore, the two most effective steps are to translate the text to create linguistic consistency, A, and to use domain adaptation to handle the contextual differences in the videos, C. Question 16. You are designing a chatbot using a transformer-based LLM that needs to generate natural and contextually appropriate responses during a conversation. What aspect of transformer-based models ensures that the chatbot's responses are coherent and contextually relevant? A. The model's ability to memorize common phrases from the training data. B. The use of only the most recent part of the conversation to generate responses. C. The use of a fixed response template for consistency. D. The self-attention mechanism that considers all previous parts of the conversation when generating a response. Okay, so this question gets to the very heart of what makes modern chatbots powered by transformers so good. It's asking for the specific magic ingredient that allows them to remember the context of a conversation and give responses that make sense. Let's quickly go through the options that are incorrect. Option C, using a fixed response template, describes how very simple, old-fashioned chatbots work. They are rigid and can't handle a natural, flowing conversation. Option A, memorizing common phrases, is something the model does, but it doesn't explain how it knows when to use a particular phrase to be contextually relevant. Option B describes a major weakness of older AI models, like simple RNNs, which had very short-term memory and would quickly forget the beginning of a conversation. Transformers were specifically designed to solve this problem. This leads us to the correct answer, option D, the self-attention mechanism. This is the key innovation of the transformer architecture. You can think of it like this. When you are in a conversation and about to speak, your brain doesn't just respond to the very last thing someone said. It instantly weighs the importance of everything that came before, the topic that was introduced at the start, a key point made 5 minutes ago, and the specific question just asked. You pay attention to different parts of the conversation's history to form a coherent reply. The self-attention mechanism allows the AI to do the exact same thing. For every new word it generates, it can look back at the entire conversation history and decide which previous words are the most important for context. This ability to weigh the importance of all previous parts of the conversation is what allows it to stay on topic, remember key details, and generate responses that are truly coherent and relevant. Question 17. You are analyzing a large dataset of customer purchasing behaviors to identify patterns that could inform marketing strategies. The dataset includes numerous features, such as customer demographics, purchase history, and browse behavior. Which data mining or visualization technique would be most effective for identifying clusters of customers with similar purchasing patterns? A. Principal component analysis, PCA. B. Regression analysis. C. K-means clustering. D. Decision trees. Okay, this question is very direct. We have a customer dataset and the goal is clearly stated. Identifying clusters of customers with similar purchasing patterns. The keyword here is clusters. We need to find the technique that is designed for this specific job. Let's look at the incorrect options first. Option B, regression analysis, is used to predict a continuous numerical value. For example, you would use regression to predict how much a customer will spend next month. It doesn't group customers. Option D, decision trees, is typically used for classification, that is, predicting a category like will churn or will not churn. Both of these are supervised learning techniques used for prediction, not for grouping data. Option A, principal component analysis, PCA, is a dimensionality reduction technique. It's used to reduce the number of features, columns, while trying to preserve as much information as possible. While you might use PCA as a pre-processing step before clustering, PCA itself doesn't create the clusters. This brings us to option C, K-means clustering, which is the correct answer. The name itself gives away its purpose. It's an unsupervised learning algorithm whose sole goal is to partition a dataset into a pre-specified number of clusters, the K. It works by grouping data points, customers, together based on their similarity across various features. This is exactly what the question asks for, finding natural groups in the data so that marketing strategies can be targeted more effectively. Question 18. You are developing a multimodal generative AI model that combines text and image inputs. After initial testing, you observe that the model performs exceptionally well on the training set but poorly on the validation set. What is the most effective approach to mitigate this issue? Increase the number of epochs for training. B. Add dropout layers during training. C. Switch to a simpler model architecture. D. Increase the size of the training set by collecting more data. Okay, the situation described here is a classic scenario in machine learning. When a model performs great on the data it has already seen, the training set, but poorly on new, unseen data, the validation set, we call this overfitting. Essentially, the model has memorized the training examples instead of learning the general patterns. Now, let's look at the options to fix this. Option A, increasing the number of epochs, means training for a longer time. If the model is already overfitting, training it longer will almost certainly make the problem worse. It will just memorize the training data even more perfectly. Option D, increasing the size of the training set, is a very effective way to combat overfitting. With more data, it's much harder for the model to memorize everything. However, collecting more data can be expensive and time-consuming. Option C, switching to a simpler model architecture, is also a valid solution, as a simpler model has less capacity to memorize. However, this brings us to option B, add dropout layers, which is the most effective approach in this context. Dropout is a regularization technique specifically designed to combat overfitting. During training, it randomly drops out or ignores a fraction of the neurons in a layer. This forces the other neurons in the network to learn more robust features and prevents them from becoming too codependent. It's a change you can make directly in your code without needing to gather more data or completely redesign your model. For this reason, it's considered one of the most effective and standard first-line defenses against overfitting. Question 19. You have deployed a multimodal AI model that processes both video and audio data to generate real-time subtitles for videos. During user testing, it is observed that the generated subtitles sometimes lag behind the video or appear before the corresponding audio is played. What could be causing this issue? Select 2. A. The model's input data streams are not synchronized. B. The model was trained with different batch sizes for video and audio data. C. The model's architecture doesn't support real-time processing. D. The model's inference time is inconsistent. E. The model was trained with an insufficient amount of video data. So, the core problem here is timing. In a real-time subtitling system, everything needs to be perfectly in sync. The issue described, subtitles lagging or appearing too early, points to a breakdown in this synchronization. We need to find 2 likely causes for this. Let's first rule out the options that don't quite fit. Option B and Option E are both issues related to the model's training phase. Different batch sizes, insufficient data. These would likely affect the accuracy of the subtitles, not the real-time synchronization. Option C suggests the model is just too slow for real-time processing. If this were the case, you would expect the subtitles to always lag behind. It doesn't explain why they sometimes appear before the audio. This leaves us with the 2 most probable causes, A and D. Option A is that the model's input data streams are not synchronized. This is a very likely culprit. The system gets a video stream and an audio stream. If there's a delay in processing one but not the other, they can be out of sync before they even get to the AI model. The model would then correctly generate subtitles for the audio it received, but because that audio doesn't align with the video frame being shown, the subtitles appear at the wrong time. Option D is that the model's inference time is inconsistent. Inference time is the time it takes the model to generate a subtitle for a chunk of audio. If this time varies, for example, it takes 0.5 seconds for a simple sentence but 1.5 seconds for a complex one with background noise, then the subtitles won't be delivered at a steady pace. This inconsistency in processing time would cause some subtitles to be ready late, a lag, and others to be ready early relative to the video, explaining the variable out-of-sync behavior. So, the problem could either be with the data going into the model, A, or with the variable speed of the model's processing itself, D. Question 20. You are building a conversational AI system using NVIDIA Riva that integrates ASR, NLP, and TTS models. Users are experiencing delays in responses during conversations. What is the most effective approach to minimize latency in this pipeline? Use a batch processing approach to handle multiple requests simultaneously. B. Increase the model sizes for ASR, NLP, and TTS to improve accuracy. C. Deploy the ASR, NLP, and TTS models on separate servers to distribute the load. D. Optimize the models for low-latency inference and deploy them on GPUs. So, the core problem here is latency or lag. The chatbot feels slow because the pipeline from listening, ASR, to thinking, NLP, to speaking, TTS, is taking too long. We need to find the best way to speed up this whole process. Let's look at the options that won't work or would make things worse. Option B, increasing the model sizes would almost certainly increase latency. Bigger models are more accurate, but they are also slower to run. This is the opposite of what we want. Option A suggests batch processing. Batching is great for improving overall throughput, how many users the system can handle per minute, but it's bad for single-user latency. It would mean a user has to wait for their request to be grouped with others before it's processed, which adds delay. Option C suggests putting each model on a separate server. While this might seem like it's distributing the load, it introduces network latency. The data has to travel over the network from the ASR server to the NLP server, and then again to the TTS server. This added network travel time would likely increase the total end-to-end delay for a single conversation. This makes option D the most effective approach. Optimize the models for low-latency inference and deploy them on GPUs. This is a two-part solution that addresses both software and hardware. Optimize the models for low-latency inference. This means using techniques like quantization or pruning to make the models smaller and more efficient without losing too much accuracy. It's like tuning an engine to make it run faster. Deploy them on GPUs. GPUs are specialized hardware designed to run the mathematical operations required by AI models much faster than general-purpose CPUs. This is like putting that highly tuned engine onto a professional racetrack. This combination of software optimization and hardware acceleration is the standard and most effective way to reduce processing time and minimize latency in real-time AI applications like the Riva chatbot described. Thanks for watching. If you found this video interesting and helpful, please like, share, and subscribe to our channel. See you in the next video. Happy learning!